Bom dia, tudo bem? Fernando, obrigado pela introdução e muito obrigado por sua hospitalidade nos últimos 6 meses. Agora eu vou falar inglês. It's been a really nice visit. Had a really nice time. I'm going to talk a little bit today about, or a lot, I guess, today about what I've done while I was here in the laboratory. And I came here with the idea of using some nanoparticles that we are synthesizing at the University of Montana to modify silica surfaces and to use those modified silica surfaces in solid phase extraction systems. The work, I'll take credit for it, but Julie McGettrick is the student at the University of Montana who synthesized all of these nanoparticles. And Rodrigo is the student here, or a postdoc fellow here, who has been helping me a great deal in the laboratory to get this work done. I gave a seminar about a month ago, and I talked about the types of research that we do at the University of Montana. So my research has been focused on electrokinetic separations and synthesis of materials to use in the electrokinetic separation systems. And these nanoparticles that I'll talk about today were actually originally synthesized for use in electrokinetic chromatography. The other research we do at the University of Montana is in environmental chemistry, looking at emissions from wood stoves and the effects of wood smoke exposure on health. And now, having spent 6 months here, I've begun to do some research in the area of sample preparation, specifically solid phase extraction. And so, I guess you can see that. So solid phase extraction, I think everyone here is probably familiar with it in one form or another. But the basic idea is to have a cartridge which is filled with a sorptive material of some kind. And the idea of that sorptive material is that it will adsorb the analytes of interest, adsorb those molecules that we want to analyze, so that we can then extract them from some matrix and analyze them often by chromatography, but also by other methods. So the typical procedure is to start with a cartridge that's packed with that material, to condition the material so that it's prepared and ready to adsorb the molecules of interest, and then to introduce the sample, which we call load, so loading the system with the sample. The sample is in a matrix, and it may contain other compounds that are not of interest to the analysis. So then next step would be to wash that material, to wash off those compounds that are not of interest in the analysis. And then finally we would do an elution step where we desorb the material or the analyte from the material in the column. And once we've done that, we have our analyte collected in a solvent that we can hopefully use. We might do some sort of solvent exchange or some kind of derivatization before analysis, but that's coming after the solid phase extraction. So this is the solid phase extraction step that we're interested in. And this material that's inside the column is really the heart of the whole process. Without a material that will give us high capacity and allow us to adsorb our analyte molecules, allow us to recover the analyte molecules after they've been adsorbed, and also allow some sort of selectivity where we can wash off those unwanted compounds, we would not have a system that works. So we have to have good materials to make this system work. So the concept that I had coming here was to develop materials sort of like this. This is obviously just a cartoon, but we have silica, and silica is the substrate that is used for most of these solid phase extraction devices, either in a form of a fiber or in the form of a capillary or as particulate matter or particles like this. And silica has, at sort of intermediate pH, it has a negative charge on the surface because the silanol sites will dissociate and leave anionic sites on the surface. So the idea was to prepare cationic nanoparticles and have them adsorb to the surface through ionic interactions and be immobilized on the surface. And these nanoparticles would then be the material that actually interacts with the solutes and extracts the solutes from the matrix. So the nanoparticles offer some really nice features. They might, and part of what we're trying to determine is just how much affinity do they show for our analytes. They should show high capacity because of their dimensions. And they should also show rapid mass transfer because when you get down to nano-sized materials, mass transfer to and from those materials is very fast. So hope to take advantage of those properties of the nanoparticles after adsorbing them to the surface. The nanoparticles that we're talking about, we synthesize at the University of Montana, and they are aggregates of a AB block copolymer. So it's a polymer with an A block, which is ionic. In this case, I've shown positive signs. It's cationic block on the polymer. And then a second block, which is hydrophobic. In this case, I've shown butyl acrylate as the hydrophobic monomer. And so we have an amphiphilic polymer, and these amphiphilic polymers will aggregate into nanoparticles. And we can synthesize and control the size of the nanoparticles. We do that primarily by changing the length of the hydrophobic polymer. So we can have a large hydrophobic region in the core of a large nanoparticle, or a much smaller hydrophobic region in the core of a smaller nanoparticle. These polymers are synthesized, they're block copolymers, they're synthesized by a specific type of polymerization known as reversible addition, fragmentation, transfer polymerization. It's a free radical polymerization mechanism, but it's one that allows us to really control the structure and the size of the polymers very carefully. So on this slide right now, all we're seeing is just the standard free radical polymerization mechanism. So we start with a monomer and an initiator. We initiate the polymerization by the reaction of that free radical initiator with the monomer, and then that free radical will interact or react with another monomer to form a growing polymer chain, which is an active free radical in solution. And this process continues and goes on quite rapidly because free radicals, as you know, are very reactive. And the process is terminated when two of these growing free radical chains find each other in solution and react to stop the polymerization. And what you end up with then is a polymer chain which is no longer a free radical and can no longer be initiated. You can't initiate it in a second process to continue the polymerization. So we call it a dead polymer. The problem with this approach for us is, first of all, that you tend to get very polydispersed polymers. So there's no controlling when these two polymers growing chains will find each other. So we might find short chains reacting to form a small polymer or longer chains reacting to form a larger polymer. And so you get a very polydispersed mixture of many different molecular weights. The other problem is that it is in fact a dead polymer. So we can't use that to make a block copolymer like we want because we cannot reinitiate the polymerization. So what we use is raft control of the polymerization, and the trick to this process is this chain transfer agent. Chain transfer agent has the ability to stabilize a free radical. It has a stabilizing group, Z, which in our case is a substituted sulfur group, and it has a leaving group, R, which can leave the chain transfer agent as a free radical. So we initiate the polymerization the same way, but we use a very low concentration of initiator. Once we initiate the polymerization, we start to get a growing polymer chain like this. And that growing polymer chain will react with the chain transfer agent. It forms this intermediate, called 2 here, numbered 2 here, but it forms this intermediate, which is a fairly stable structure, stabilized by this Z group. The R group is a good leaving group, and so the R group will leave as a free radical. And that free radical can initiate additional polymerization. So basically essentially most of the polymerization is initiated by this process here, where we're using this free radical that came from the chain transfer agent to initiate the polymerization. And what that means is that the number of growing chains is nearly equal to the number of chain transfer agents. So most of the growing chains in this system are actually in this form, where the growing polymer chain is capped on the end by the chain transfer agent. And then what we have is a small concentration of growing polymer chains in solution, which will react with the chain transfer agent, form this intermediate, displace the other chain, which starts to grow, and this process goes back and forth, allowing each of these chains to grow at about the same rate. And so over time, what happens in this system is we have these polymer chains growing slowly, much more slowly than in an uncontrolled free radical polymerization, and forming relatively monodispersed polymers, which do not have a great deal of range in molecular weight. We also have most of our polymer in this form. So when we stop the polymerization, what we get is a living polymer, a polymer that can be reinitiated through this process up here, can be reinitiated, and we can start this whole process again and add a separate monomer. So that allows us to do the block copolymerization. Lastly, the concentration of these free radical polymers in solution is actually very low. Remember, most of the polymer growing chains are in this form, and only a small concentration is in this form. So the chances of those two polymers finding each other and terminating to form a dead polymer are actually quite low. So this process, it happens, but it's not a major part of the polymerization process. So this controlled free radical polymerization allows slow polymer growth, very little termination by this process. We get monodispersed polymers, and at the end of the process, we get a living polymer that we can then continue to or initiate another polymerization with. We use this process in a technique called ab initio raft in emulsion polymerization. It was developed in Australia at the CSIRO in Australia, which is one of their national laboratories. And the same idea, we start with this chain transfer agent, but we start with a hydrophilic monomer, ionic monomer, and we form a hydrophilic block. So we form a hydrophilic ionic polymer, which is a living polymer with the chain transfer agent end at this end. And then, in this case, I'm showing it with the acrylic acid as the ionic monomer. We can stop this process, we can collect this polymer, and we have an active living polymer that we can then initiate and polymerize further. And so we initiate that in a second step of the polymerization, where we use a hydrophobic monomer. In this case, I'm showing butyl acrylate as the hydrophobic monomer. And we can then add a second block to the polymer. So we have our ionic block and our hydrophobic non-ionic block. And as that polymerization takes place, they will start to self-assemble into micelle-like structures. And as the polymerization of the hydrophobic monomer continues, it will take place in the core, the hydrophobic core of this micelle structure, and form stabilized nanoparticles. So that's how we make these nanoparticles. The nice thing about this process is that we have a lot of control over what chemistry we use for the hydrophilic block and for the hydrophobic block. And we can also, because this is controlled polymerization, we can control the length of the hydrophilic block and the length of the hydrophobic block. So we have a lot of control over the structure and chemistry of these particles. All right, this is just showing that we do have the, I don't know if it gets any better, but if we do have the capability to stop the polymerization after that first step, this is an anionic hydrophilic polymer, and this is a cationic hydrophilic polymer that we've polymerized by the raft polymerization. They're analyzed by MALDI-TOF mass spectrometry, and what you see is we get an envelope of polymers of different chain length, and we can calculate what the average chain length is. So in this case it was 11, in this case it's 7. And you can see that there's some dispersity in this, that it's not just one polymer with a degree of polymerization of 7, but it's 7 plus or minus 2 or 3, something like that, in terms of the degree of polymerization. The polymers that I'll talk about today are primarily of this structure. So we have a butyl acrylate hydrophobic block, and we use this AET-MAC, or acryloxy ethyl trimethyl ammonium, as the hydrophilic block, and it's a cationic, permanently cationic material. We developed this for electrokinetic chromatography applications, and we developed it knowing that those nanoparticles would adsorb to the negatively charged capillary wall, and they would reverse the electroosmotic flow. That's what we wanted to achieve with this system. And just a quick step away from that, we had already demonstrated that with anionic nanoparticles, we could achieve very nice separations using nanoparticle materials in electrokinetic chromatography. But as soon as we put these cationic nanoparticles into the system, we started to get separations that looked like this. And this is, of course, not at all what we wanted. And what we realized is, after first considering that maybe the cationic nanoparticles just were not going to work, what we realized ultimately was that what's causing these big broad peaks and this retention is actually interaction of these hydrophobic analytes with the nanoparticles that are absorbed on the capillary walls. It's not something we wanted to have happen, but it is what's happening. And so that causes this retention. It's a bad thing for electrokinetic chromatography, but it occurred to me and to my student that we might be able to take advantage of this in other types of systems. We could use these nanoparticles to modify the silica surface and make it have a high affinity for hydrophobic compounds. Since I've been here, Julie, the student, has done a very nice job of fixing this problem. And what she does is to modify the capillary walls first with this homopolymer, which is not hydrophobic, and then we can use those cationic nanoparticles and get very nice high-efficiency separations again. So this demonstrates clearly that it was the interaction at the capillary walls that was causing the problem, and that those interactions at those capillary walls are quite strong. So to return to our concept, we wanted to use silica and adsorb these nanoparticles onto the silica surface, and we've already demonstrated using the IQSC results that we should expect some high affinity interactions with those modified surfaces. The question was, coming here, how stable are these coatings, and also just how much affinity do we have, and for what types of compounds can we do these types of extractions? We're not the first people to use nanoparticles in separation science, of course, and not the first to think about using nanoparticles to modify a surface. The group at the Australian Centre for Research on Separation Science, ACROSS, in Hobart in Tasmania, multiple authors over a period of 3 or 4 years, they demonstrated that you can take ionic nanoparticles like these, adsorb them to a polymer monolith, and get high capacity, high efficiency separations by ion exchange. So they're ion exchange separations. And this is in fact the chemistry that Dionex uses for most of their high capacity ion exchange materials now. They use a polymer packing material, and they modify it with ionic latex nanoparticles. And then more recently, some interesting work where this author took silica surfaces and he adsorbed nanoparticles to the outer surfaces and had C18 octadecyl silane modification of the pores. And so he was able to develop mixed mode materials where he had ion exchange at the nanoparticles on the outer surfaces and reversed phase interactions with the C18 down in the pores. So there is some evidence clear that we could do some sort of ion exchange type separations in some cases. All right, I came here with several different nanoparticles that had all been synthesized by Julie. We've evaluated 4 of these. 2 of them have aromatic functionality in the hydrophobic core region. And 2 of them have just butyl acrylate in that hydrophobic core region. The butyl acrylate materials differ in terms of the length of this cationic, the degree of polymerization of the cationic group, and also in the overall size of the nanoparticles. All right, the first experiments we tried to do, and Mariani and Mady both helped me quite a bit with these studies, was to adsorb the nanoparticles on the inside of a capillary, fused silica capillary, and attempt to do in-tube solid phase microextraction using the nanoparticle-modified capillaries. Started here because I know that these nanoparticles would interact with and modify the surface of the capillaries. I just didn't know whether we would get enough material to do any kind of solid phase microextraction. So we were able to get some electron microscopy done on the nanoparticles on the inside of these silica capillaries. And it takes a little bit of imagination, but if you compare this picture or this image to one for a uncoated silica capillary, the difference is these discs adsorbed onto the surface. And so if we convince ourselves that these are the nanoparticles, what looks like is happening is the nanoparticles are adsorbing to the surface and collapsing and forming a very thin, flat disc on the surface, and that there's a great deal of unmodified silica in between the nanoparticles. So we're not getting a complete coating of the surface, if this image can be believed. What we're getting is a lot of different small discs immobilized on the surface. All right, we tried to use this for the extraction of ochratoxin A. We'll come back to this compound later. And various attempts with various nanoparticles, we really never found any evidence that we were getting a good extraction of the OTA from aqueous matrices. So a little bit discouraging, but probably because we don't really have a thick uniform coating on the surface of the capillary. And so the capacity and the phase ratio in this case is going to be relatively poor. So we moved on from there to start to do some solid phase extraction on porous silicas. And so the idea is to increase the surface area available, change that phase ratio, and get to a point where we can really start to measure the interactions of our solutes with the nanoparticles coated on the silica particles. And so we set up an inline solid phase extraction system where we could do a series of experiments to measure these interactions. Rodrigo was a huge help in this part of the work because he was able to quickly design and help me set up 2 different instruments to make these measurements. We started with this instrument here, instrument 1, where we had a single 10-port valve. And the idea here was that we would fill loop A with our analyte solution. Here's our solid phase extraction column. Here's a detector after the solid phase extraction column. We have a pump here. We're continuously pumping mobile phase or solvent through the solid phase extraction cartridge. We could fill our loop with our sample, inject the sample, and let it be adsorbed onto the solid phase extraction cartridge. And then we could fill loop B with a elution solvent and inject the elution solvent and force our analyte molecules off of the solid phase extraction column and into the detector. We could measure the extent to which that had worked. This worked out reasonably well, but we moved on pretty quickly to this system where we actually set it up where we're using a syringe pump to continuously introduce our sample solution onto the solid phase extraction column. So we have an HPLC pump pumping a solvent, a mobile phase. We can switch this valve and switch it to where now we're pumping our analyte solution onto the solid phase extraction cartridge. Still have a detector after the column. And then we have a second injection valve in here where we can inject our elution solvent. So we can inject small volumes of elution solvent after we have loaded the column with our analyte. We can then elute it using this elution solvent. And so the difference here is that we're using a continuous introduction of the sample, and we are also using this system to coat the silica particles in the SPE column. So we pack the column with bare silica particles, and then we inject a volume of our nanoparticles suspended or dissolved in solution. We fill this column with those nanoparticles and let it sit for a period of time, and then we rinse those nanoparticles out and start to do the rest of the experiments. This is a frontal analysis type experiment where we're monitoring the signal from the detector while we're continuously introducing our sample into the system. All right, the columns we used here are 45 millimeters in length, 2 millimeters inside diameter. They were packed with 40 micrometer porous silica particles, bond dilute silica. They have a 60 angstrom pore size, and that's something to think about because the nanoparticles we think are a nanometer scale, tens to hundreds of nanometers, so they would not immediately be able to get into those pores. We coated these particles with the nanoparticles. We used an 8% solution of the nanoparticles when we could to fill the column. We leave that for 72 hours, which turns out to be from Friday afternoon to Monday. And then we would rinse the nanoparticles out, and we would move on to start doing some sample introduction. Samples were introduced at 300 microliters per minute. We monitored the absorbance and analyzed the elution fronts that we observed, and we would elute the solvent or elute the samples from those analytes that were adsorbed to the column. We could elute them back off with 0.2 milliliters of solvent. We started out trying to use 100% acetonitrile or 100% methanol, and we lost about a month of work, probably a couple weeks of work, because every time we would inject 100% solvent into this system, it would degas, and we would get air bubbles in the detector, and it would take about an hour to get the detector to settle down and start to work again. So we eventually realized that if we just went to 90% methanol, it was still effective at washing the column, but we didn't get the air bubbles in the system, and we could do a lot more experiments. So this is what a typical elution profile looked like as we did these experiments. We're starting right here where you see that big spike. We're we're switching that valve and starting to introduce 500 parts per billion naphthalene in water. We don't see any absorbance for the naphthalene for some period of time. This is a column, the silica that was coated with one of the nanoparticles. And we don't see any signal for the naphthalene for some period of time, greater than 15, 16, 17, 18 minutes here. And then we start to see the signal go up as the naphthalene breaks through the column. And it goes up and eventually will stabilize at the maximum concentration. This is the signal you would get for 500 ppb naphthalene. So if you were using this in a solid phase extraction system, it's this region here where you would be able to get 100% recovery because none of the naphthalene has started to break through yet. And if you think about this in terms of standard chromatography, this would be our retention time here to the inflection point of this elution front. And this retention time does not change with concentration. The maximum signal here changes with concentration, but this time zone here, as long as we're working within the linear region of the chromatography, does not change. So I apologize for the mix-up in the colors, but if we take the first derivative of this orange trace here, what we get is this green peak. And the maximum value in this peak comes at the inflection point of that front. So this is what you would expect to see if you had injected it as in chromatography as a peak. You'd see a peak like this, and this is just a representation of what the chromatography would look like. What we can do then, by collecting these fronts, taking the derivative, you get a lot more noise, of course, when you take the derivative, so we have to smooth out the signal. But then we can look at different retention times and retention factors as a way to evaluate different surfaces, different materials, and utility for different types of molecules and analytes. All right. I mentioned that I came with a series of nanoparticles and that these are the ones that we used. First thing that we noticed in the first weeks of doing these experiments is that when we coat the silica with these nanoparticles, we get a very highly stable coating. We don't see changes in retention of analytes over time. We can reproduce our experiments over and over and over again. And in fact, we have one column which is coated with this nanoparticle number 47 that we've used since February, and we're still using it just a couple weeks ago, and we're still getting the same amount of retention. We've done probably 100 different injections on the system, and we've exposed it to lots of different solvents, high pH, low pH, and it remains a very stable modified surface. So that's really good news. We also, of course, went and did the experiments where we ran our retention experiments with bare silica without any nanoparticles on the silica. And the nanoparticles do have a significant effect. So what we're seeing in terms of retention is really retention caused by the modification by the nanoparticles on the surface. We've done almost all of our work with these two nanoparticles, these two butyl acrylate nanoparticles, because when we tried to do some experiments with the aromatic nanoparticles, we got very poor performance. We don't know yet why that might be the case. I think that part of the problem is that these were very difficult to synthesize, and so what I brought with me were low concentration solutions at less than 1% nanoparticle in solution. So we're not modifying the silica surface with an 8% solution the way we are with the other nanoparticles. So that may be part of the problem. In any case, all of our usable results came with these two nanoparticles. And in general, nanoparticle 47 gave about 2 or 3 times as much retention or affinity for the analytes as did nanoparticle 32. And obviously this is very preliminary data. We don't have a lot of data to look at and to try to work out what's causing all of this. But the big differences between these are the ratio between the hydrophilic ionic block and the hydrophobic non-ionic block. Here we have a longer hydrophilic block and a shorter hydrophobic block. And here we have a shorter hydrophilic block and a longer hydrophobic block. So we're actually coating the surface with a more hydrophobic material with less ionic character, but still sufficient ionic character to allow the material to adsorb to the surface and remain there in a very stable form. All right, some things that we investigated early on. We wanted to make sure that we really were working in that linear region where retention is not a function of concentration, and we found that for naphthalene, we could vary the concentration of the naphthalene between 0.25 and 2 parts per million and not see any change in the retention. And so we use typically 0.5 or 1 part per million solutions for all of our studies from that point on. we wanted to make sure that that front, which is not very sharp, as you noticed, we wanted to make sure that that front was not being affected by the flow rate through the system. So we looked at flow rates between 100 and 600 microliters per minute. And again, we found no effect of the flow rate. So we did all of our experiments from that point on at 300 microliters per minute. We did try to use some large pore silica with larger pore size, to see if we could get more nanoparticles adsorbed down inside the pores. And performance was not at all improved with that material. So either because the material had lower surface area or because it really isn't an important effect, the large pore silica was not something that worked out for us. If we coat different columns with the same nanoparticle chemistry, we don't get exactly the same response. We do get pretty reproducible response if we use this 72-hour coating, and we do get pretty much optimal performance for that particular nanoparticle when we use that coating. But we still see changes in retention factors of up to a factor of 2 between different coating procedures. And so this is something that would really have to be worked out before this could be considered a real viable approach. Retention, however, for a given column is actually quite reproducible. It's less than 5%. Maximum measurable retention factor was about 60. Beyond that, it just takes so long to do the experiment, and the front becomes so diffuse that it's impossible to really get good results. And we were able, typically, to get all of the material back that was adsorbed to the column to be desorbed by using 1 to 3 injections of 90% methanol. So we could bring the column back to its native state by washing with the 90% methanol. All right, let's look at some of the actual results. The clock is apparently not working at all. So I still have half an hour. Okay. We looked at benzene, toluene, ethylbenzene, xylene. These are obviously components of gasoline, and they are often found in groundwater around gasoline stations and refineries and places like that. So it's an interesting problem. We looked at the retention of benzene from water on a column coated with particles, the nanoparticle 47, and a column coated with the nanoparticle 32. And we do see some significant retention of these compounds, and we also see that 47 is outperforming 32. And then if we compare that to commercially available materials, so in this case we're looking at an octyl C8 modified silica. Benzene has much higher retention on the C8, toluene much higher retention. For ethylbenzene and xylene, it was above our ability to measure it, so it was very high retention. So we do see extraction of these types of compounds. We could use these nanoparticle-coated surfaces to extract benzene or BTEX from water, but in fact, the performance of the nanoparticle surfaces is much less than that of conventional commercially available C8 or C18 materials. We try to do this experiment with C18, even benzene exceeds our ability to measure the retention factors. So we do see interactions, but much weaker than with octadecyl or octyl modified silicas. One thing that was a little interesting is that if you look at the retention of benzene, toluene, xylene, and ethylbenzene, first of all, xylene and ethylbenzene were reversed on 47 relative to 32, so some strange, possibly interesting selectivity differences. But if you made a nice high-efficiency column with this system where you didn't have so much peak broadening, you could achieve a separation of these 4 compounds using just water as the mobile phase. So in column 32, you could do it even faster than you could with the material 47. So one potential application of these materials might be for that sort of an application where you would, instead of using high organic modified mobile phases, you could just use an aqueous mobile phase for the analysis of compounds like BTEX. We're interested in, what really is the mechanism of retention. So we looked at a few different things with all of these studies. One was we looked at the logarithm of that retention factor as a function of the logarithm of the octanol water distribution coefficient. And what we see when we make these plots is we see linear plots, a linear relationship between log retention factor and log partition coefficient. And that's typical when the primary retention mechanism, the primary interaction mechanism, is based on the hydrophobic nature of the molecule. So it looks like we're really seeing sort of a hydrophobic interaction, reversed phase type material, but with much weaker interactions than what you have with C8 or C18. We continued this with polynuclear aromatic hydrocarbons. The retention of these PAHs was too high if we did aqueous mobile phase or aqueous media. So we made all of our measurements in 50% methanol. This brought the retention factors down into the range where we could measure them. And then we looked at column 47 and column 32 again. Much more retention in column 47 than in column 32, and increase in retention as we increase the size of these PAHs. This is 2 rings, 3 rings, 4 rings in sort of a, a symmetrical structure, and 4 rings in more of a linear structure, and then 5 rings, which I haven't shown on here because the retention factors were too high to measure on column 47. Anyway, we see an increase in retention as we increase the size and hydrophobicity of the PAHs. If we compare the performance to C8 and C18, the purple bars here are C8, the green bar here is C18, and so again, conventional commercial materials really far outperforming the nanoparticle-coated surfaces for the retention of these types of compounds. That's perhaps a bit of a negative result, but on the positive side, if we don't use 50% methanol, if we're looking at aqueous matrices, we get sufficient retention of naphthalene and all of these other PAHs to actually do an analysis and to do pre-concentration and extraction for these PAHs. And because the interaction is not quite as strong as it is with something like C18 or C8, it's a lot easier for us to elute, to desorb the PAHs from the nanoparticle-modified column. So there may be some advantage in terms of ease of recovery of these compounds after they've been adsorbed to the surface. Again, looking at logarithm of retention factor versus the logarithm of that octanol water distribution coefficient, linear plots, again, indicating primarily the interaction is based on hydrophobic effect. And the fact that this is linear even out to 6 rings in the polynuclear aromatic hydrocarbon implies that we're not reaching some limit where the size of the molecule is exceeding the ability of the nanoparticle to solvate it. So size is apparently not really a limiting factor, at least in this range. On column 47, we looked at the effect of the addition of methanol. So we plot the logarithm of the retention factor versus the concentration of methanol. Again, only 3 data points here, but a nice linear relationship, which is, again, typical of the reversed phase retention mechanism for simple compounds like this. So what we're apparently seeing is primarily hydrophobic interactions and reversed phase type selectivity. But not really competitive with C8 or C18. So next question was, is there some other feature of these nanoparticles which would give them an advantage for the extraction of particular types of compounds? And so we started to look at, could we use a mixed mode retention mechanism? The nanoparticles are cationic, so and they're also hydrophobic, we know that. So if we could use or extract a molecule which is anionic, we might expect to see strong ionic interactions as well as the hydrophobic interactions to retain the molecule on the surface and also to give us a high degree of selectivity. So We looked at sulfoquinoxylin as an example. This is a compound which is anionic at higher pHs and neutral at lower pH. It has an octanol water partition coefficient in the neutral form of 1.55, so not terribly hydrophobic. We could look to see whether ionization of this molecule would, in fact, cause higher retention. And so we looked on both of our columns, column 47 and column 32, at low pH where it's neutral, at high pH where it's anionic, and in fact we see less retention of the anion. So apparently there's no strong ionic interaction with the nanoparticle which will increase or cause higher retention of anions on the surface. It could be, if you think about that electron microscopy slide, it could be that we're still not getting a fully uniform coating of these silica surfaces, and so we actually have a silica surface which is in part anionic and is not going to be very attractive to the anionic molecules. It's just really hard to know at this point exactly what's going on, but for sure these particular surfaces are not retaining anions. We looked at a series of steroid hormones which are fairly hydrophobic, hydrophobicity up similar to that of some of the more hydrophobic PAHs that we looked at. We anticipated seeing very strong retention of these compounds and that perhaps this would be an interesting application of these materials. And in fact, we did see retention, but we saw very weak retention relative to what we had expected, and also much, much weaker than C8 or C18. And estriol, the one compound here, extremely low compared to the others, and it's really not particularly clear why. These are the structures of these compounds, and so the one thing about estriol that's different from the other two is that it has hydrogen bonding, polar groups on both ends of the molecule, whereas these molecules do not. And so it may be that that is the deciding factor here, but for some reason, estriol has very, very weak interactions with our nanoparticles, and this turned out not to be a suitable application. If we take all of the data that we've got for various different compounds, all the aqueous data that we have for the different compounds, and we plot, again, the logarithm of the retention factor versus the logarithm of that octanol water distribution coefficient, we see for column 47, sort of a nice linear region up here. For column 32, a nice linear region. But then, if we try to put the steroid hormones on that same plot, they fall well outside the model or the relationship. So these compounds are giving much lower retention than what we would expect from this hydrophobic interaction mechanism. We don't know why yet. We just know that that's the case. It may be that this would be a nice feature of these nanoparticles, that they are selective for specific types of hydrophobic compounds and not very retentive toward other types of compounds, but we don't know yet exactly which compounds to expect would have high or low retention. The other thing to notice on this plot, naphthalene is this point right here for the column 47 and this point right here for column 32, and it seems to be falling above the plot for the BTEX material. So it may also be an outlier. These PAHs may actually be showing stronger retention than what we would expect relative to the BTEX series. All right, so then we looked for one last application. What might we be able to do with these nanoparticles? We looked at ochratoxin A again. It's a mycotoxin it's found in food, it's released by fungi. It's found at very low concentrations, but fortunately can be detected by fluorescence. So it's possible once you extract, pre-concentrate, that you can detect it at the very low levels it's found in food. It has a lower pKa value of 4.4. So at low pH, well below 4.4, it should be in this non-ionic form. At higher pH, it should be in this anionic form. This figure I simply stole from a presentation that Mariani sent me. And it has a fairly large octanol water partition coefficient of log partition coefficient of 4.6, so it's very hydrophobic. So what we expect is that at low pH, when it's hydrophobic, it will interact with the nanoparticles and be extracted. At intermediate pH, where it's anionic, it may actually interact even more strongly with the nanoparticles because of the ionic interactions that are available. So we looked at 500 parts per billion ochratoxin A. We looked at 2 different phosphate buffers at pH 2, where it's in this form, and pH 6, where it's primarily in that form. And I'm showing the raw data here. So the red trace and the blue trace are both at pH 2, non-ionic, 2 separate injections or 2 separate analyses. You can see the reproducibility of the analyses. You can see that we're getting significant retention of the compound for 10 minutes or so. And in fact, the inflection points out here, 17, 18 minutes or so. But then if we run the same experiment with the same concentration, the same compound at pH 6, where it's anionic, it's simply not retained at all. It just comes straight through right after the injection and stabilizes. So there is no retention of this anionic compound on these cationic nanoparticles, even though it has hydrophobic character. But there's strong retention of the non-ionic compound with that hydrophobic nanoparticle. All right, and then to sort of carry that a little bit further, there's a lot here, but the green trace is the trace where we had pH 6, so no retention, and the scale is much different here, so we can barely see the increase in the signal for the compound coming through. The red trace is one of the traces I showed you before at pH 2, and so you see for a period of time out to 10, 15 minutes before you start to actually see that signal rise due to the breakthrough of that compound. And then if we make a single injection, 0.2 milliliters of 80% methanol, we get all of this compound that was retained in this region here, all of the ochratoxin A off in a very sharp peak with an increase in the signal of about 70-fold. So we're getting a concentration increase of at least 70-fold. This is absorbance of 1.4, so I doubt that it's in the linear region of the detector. So we may actually be seeing a greater concentration factor than we see in signal. And if we make a second injection of the 80% methanol, it shows up right here, this little blip. So we're getting essentially full recovery of that ochratoxin A using a single injection, and at the front of that injection, it's just being pushed right off the column by the 80% methanol. Now, the 80% methanol is not buffered, so it's probably at some intermediate pH. And so I expect that probably what we're seeing here is a combination of the methanol pushing the material off, but also the higher pH where that compound is really not retained, helping to desorb ochratoxin A from the nanoparticles. So there is the potential to elute this molecule and a pH 6 buffer at even lower methanol concentration. This approach could be evaluated with fluorescence detection to see just what kind of concentration you would be able to detect. And it should, of course, be evaluated in the matrix of interest. One of the matrices for this analysis is wine, and wine is already 10, 12, 14% ethanol, so it's not clear just how much retention you would get due to hydrophobic interaction from wine, but that's something that would need to be evaluated. All right, so to sort of wrap up what we've done in 6 months, we coated several different surfaces with these nanoparticles, and we found that we get very nice stable coatings. We found the affinity is a function of the nanoparticle structure and chemistry, but we can't really tell you which structural factor is the most important, or we can't talk about any kind of trends because we don't have enough data. We know that we get strong affinity for hydrophobic compounds, very strong affinity for the polynuclear aromatic hydrocarbons, but that is less than that for C8 or C18. That's a disadvantage in terms of the amount that you could extract, but it's an advantage in terms of the ability to be able to desorbit and recover the PAHs. The steroid hormones were clear outliers on this whole retention mechanism concept that we have, and there may be other compounds that would also be very weak, give us very weak interactions, and this could be an avenue to look at in terms of the selectivity of these materials. Well, selectivity right there. There's no affinity apparently for the anions. As we go from a neutral compound to an anionic compound, we expected to see strong ionic interactions, and we just don't see it. It's just not there. So again, the reason for that's not entirely clear. It could be because we have a lot of bare silica, which is also anionic at those pHs, or it could be that the cationic functionality is really not accessible to our analytes. Applications, I think there's some potential there for the ochratoxin A extractions, certainly some potential for PAHs because we have strong interactions with those. We know that hydrophobicity is going to be a major factor in determining the extractability or the affinity, and that brings us back to matrix. We haven't done any experiments with different matrices besides aqueous matrices. Reversed phase chromatography, it's possible, for example, with the BTEX compounds, that one could use these nanoparticles to coat, for example, a silica monolith, and then do reversed phase chromatography using just aqueous mobile phase, so no organic solvents involved. So that's something that might be worth investigating. And then there's, of course, many, many different additional solid phase extraction formats that could be looked at. Solid phase microextraction, MEPS, different types of devices and different types of configurations that one could investigate. Okay. Certainly want to acknowledge the people that made all this possible. So Professor Lansas, again, very hospitable, gave me space and time and support for all of this work. Students in the lab, Mariani, Mady, and Marisa were all very helpful. Rodrigo was incredibly helpful, did so many of these, set up so many of these instruments and experiments for me, made it possible to get all of this work done. The Fulbright Foundation for funding for the first 4 months, FAPESP for funding for the last 2 months, and of course, my wife Janet, who is willing to travel halfway around the world with me so that I can do these types of things and disrupt her life to do that. And then I'll leave you with some photographs that we took around Brazil during our travels. I did get some experiments done in the lab, but I spent probably almost as much time out traveling around and exploring Brazil. And we saw a lot of really interesting and fascinating things and met a lot of really very nice and helpful people. So we've enjoyed our 6 months in Brazil immensely. And with that, I'll leave it for any kind of questions anybody might have.
Professor, if I try, for example, another analytes more polar than PEGs and oxytocin A, and maybe the results can be better with better rotation or not?
So the polar compounds, now, all the data we have till now indicates that the primary interaction mechanism is due to the hydrophobicity of the compounds. So as the compounds become more polar, they become less retained on this nanoparticle surface. Now, we didn't try a lot of really polar compounds because we sort of made that observation and thought, well, going to very polar compounds is probably not going to be worthwhile.
But with intermediate, maybe, or with intermediate polarity?
Yeah, possibly. Yeah.
And another question is possible to functionize surface of nanoparticles with another kind of materials?
Certainly, there's a lot of different types of monomers that one could use to synthesize these nanoparticles. And one of the things that one of my students is working on right now is anionic chiral monomers in order to put chiral centers onto the nanoparticles and then hopefully get an enantiomeric selectivity to be able to separate enantiomers. But yes, there's a lot of different types of structures that could be utilized as the head group. We've used a simple cationic shell chemistry here because we wanted to get those interactions with the anionic silica surface. But in the proposal to the Fulbright Foundation, we also mentioned that if this interaction was not strong enough, that one could synthesize these nanoparticles with a reactive group, which would allow covalent attachment to the silica surface. And so there's a lot of different types of chemistries that one could use for that shell chemistry, which would affect the type of immobilization that you have on the silica, but could also affect the strength of the interaction of various analytes with the nanoparticle. Right now, my impression is that cartoon of that spherical nanoparticle with a hydrophilic shell and a hydrophobic core is not really accurate. It's not accurate in solution, but it's certainly not accurate on these once they're absorbed onto the surface. That hydrophobic structure seems to be really accessible, and that cationic hydrophilic structure does not seem to be very accessible. Now that could be changed perhaps, but with the materials we're using right now, it looks like the analytes are really accessing that hydrophobic core region.
Did you evaluate if the particles are stable enough with all these changes of solvents and pHs during analysis? Because in ECK analysis, we use a buffer, and here we use different solvents and pHs. For example, in the case of ochratoxinate analysis.
It's a real concern. The stability of the surface has been from the beginning a real concern, but we have not noticed any degradation in performance of these surfaces over the course of these experiments. So that column 47 that I showed the results for is the same column 47 that we packed and modified in February, and we've been using it for multiple different types of injections and analyses and extractions since then. And if we go back to naphthalene, the first thing that we analyzed on it, and look at the retention of naphthalene, we get the same retention today as we did in February. So far, we've not found conditions that are destructive to these surfaces.